Section: Introduction. In this section, we discuss the advancements in video generation, which have significantly improved recently. By utilizing large-scale data and scalable models like the diffusion transformer, we now have state-of-the-art models capable of creating realistic single-shot videos lasting up to a minute. However, real-world narrative videos, such as movies and TV shows, consist of multiple single-shot segments, highlighting a gap between current single-shot generation capabilities and the needs of video content production. To address this, we propose shifting from single-shot synthesis to scene-level generation, where a scene is a series of single-shot videos that depict coherent events over time. For example, in the iconic scene from Titanic where Jack and Rose meet, there are 4 main shots: a close-up of Jack looking back, a mid-shot of Rose speaking, a wide shot of Rose approaching Jack, and a close-up of Jack embracing Rose. Creating such scenes requires visual and temporal consistency to ensure a smooth narrative flow. Visual coherence involves maintaining consistent elements like character identity, background, lighting, and color tone, while temporal coherence requires uniformity in character actions and camera movements across shots. To tackle these challenges, we introduce long context tuning, LCT, for scene-level video generation. LCT builds on a pre-trained single-shot video generation model, adapting it to learn a longer context that models cross-shot consistency from scene-level data. We incorporate 3 innovative design elements. First, we adapt the full attention mechanism to include all shots in a scene, using a unique positional embedding that maintains the relationships among video tokens. Second, we unify visual condition inputs and diffusion samples by applying independent diffusion time steps to each shot, allowing for joint denoising. Finally, we implement bidirectional attention that can be fine-tuned for efficient auto-regressive generation, reducing computational demands. After training on scene-level data, our model shows excellent performance in generating visually and semantically consistent scenes. We present a generated video with around 20 shots lasting 3 minutes, maintaining appealing visual and semantic coherence. Notably, LCT demonstrates capabilities beyond the pre-trained model, allowing for compositional generation that integrates character identity and environment images, even without explicit training for this task. Additionally, LCT supports auto-regressive shot extension, enabling interactive modifications by users. We believe our work will inspire future research in long video generation. In the related work section, we review previous studies on shot-level video generation, which initially relied on GANs and later shifted to diffusion-based methods. Notable advancements include models like Aligner Latents and Sora, which improved video generation quality. We also explore scene-level video generation, which synthesizes sequential videos of continuous events, primarily through appearance-conditioned and keyframe-based methods. Despite progress, existing methods still face challenges in modeling complex scene coherence. Lastly, we address the limitations of current single-shot video models, which typically generate short clips. We highlight various approaches to extend video length, including training-free methods and auto-regressive frameworks. Our approach directly enables long video extension through shot extension, both with and without shortcuts. Section Summary. In this section, we discuss the advancements in video generation, highlighting the transition from single-shot synthesis to scene-level generation to meet the demands of real-world narrative videos. We introduce our long context tuning, LCT, approach, which enhances cross-shot consistency by adapting a pre-trained model to learn from scene-level data, ultimately enabling the generation of visually and semantically coherent scenes. Section: Method. In this section, we aim to generate videos at the scene level, creating multi-shot videos that maintain consistency. To achieve this, we introduce long context tuning, LCT, on a pre-trained single-shot video diffusion model, allowing us to expand its context and learn scene-level relationships directly from the data. We begin by discussing single-shot video models, followed by our LCT approach, and then explore context-causal attention fine-tuning for efficient generation. Finally, we cover the implementation of training and inference. For our method, we utilize a latent video diffusion transformer model. The diffusion process transforms the original RGB video into a latent representation. During training, we create noisy samples by blending clean data with random noise. Our goal is to predict the velocity field, which involves minimizing the difference between the predicted and actual noise. The model uses a specific design that treats text and video tokens separately but combines them for attention operations. We also apply a 3D rotary position embedding to encode the position of video tokens. Next, we outline the key components of LCT for generating scene-level videos, including how we prepare data and design the architecture. We unify the conditioning inputs and diffusion samples through an asynchronous training strategy. In terms of data curation, we define a prompt structure that treats a scene as a coherent sequence of video clips sharing overarching themes while differing in shot-specific details. We use a two-tier prompt system: global prompts for overarching elements and per-shot prompts for specific events, ensuring clarity in character references. We gather scene-level video data from various public sources, segmenting raw videos into scenes and then into individual shots. Each scene video is processed to generate both global and shot-level descriptions, resulting in around 500,000 scene samples. To enhance our training data, we also filter single-shot videos with significant temporal changes, treating them as multi-shot videos, which adds approximately 1 million more samples. For learning beyond single shot, we employ full attention to model scene-level consistency without adding biases. This involves combining all text and video tokens for attention operations. When only one video is present, our model functions as a single-shot model, maintaining compatibility with single-shot data. To address the challenge of distinguishing tokens from different shots, we implement an interleaved 3D position embedding. This method allows us to maintain the relative positions of text and video tokens while distinguishing their absolute positions, ensuring that each shot retains the text-visual alignment from the pre-trained model. We also incorporate dummy video tokens for global prompts, treating them as standard text-video pairs. Section Summary. In this section, we outline our method for scene-level video generation using long context tuning, LCT, to enhance a pre-trained single-shot video diffusion model, enabling it to learn scene-level correlations from data. We detail our approach, including data preparation, architecture design, and the use of a two-tier prompt structure to capture both global and shot-specific elements, ultimately yielding a robust dataset for training. Section: Unify conditions and diffusion samples. In this section, we discuss how our model generates multi-shot videos from text prompts and how visual conditioning enhances capabilities like story extension and auto-regressive generation. Instead of using auxiliary networks for visual conditioning, we unify conditioning inputs and diffusion samples using an asynchronous time-step strategy. We assign different diffusion time steps to each shot during training, which helps create dynamic dependencies between shots. For example, if one shot has less noise, it can provide valuable appearance information to help reduce noise in other shots. This allows us to set some samples to low noise levels for visual conditioning or synchronize time steps for joint generation. Our conditioning mechanism also supports auto-regressive shot generation by using cleaner history samples as conditions. In this setup, cleaner samples rely less on noisy ones, while noisy samples draw information from the cleaner ones to maintain consistency. This means we can replace bidirectional attention with more efficient causal attention. After training our model, we implement context causal attention, which allows us to use cached features from previous samples during inference, reducing computational demands. For training, we jointly train the model on both single-shot and scene-level video data to maintain its pre-trained capabilities. We randomly replace shots with single frames at a set probability and sample diffusion time steps independently for each shot. We compute losses per shot and average them before backpropagation. When generating multi-shot videos, we recognize that cross-shot dependencies can be non-sequential. For instance, a character appearing after several shots needs to reference their initial appearance rather than just the shots immediately before. This insight leads us to a generation strategy that incorporates human selection. We create a history pool of key character and environmental shots and selectively use this pool to generate new shots based on relevance. In our experiments, we implement LCT on a text-to-video diffusion model using the MMDIT architecture, trained on images and videos at their original resolutions. We use a maximum context window of 9 shots and train on 128 NVIDIA H800s for 135,000 iterations. After LCT, we fine-tune the model for 9,000 iterations with causal attention, maintaining a training resolution of 480 by 480 pixels. We compare our approach to previous methods in scene-level video generation, focusing on appearance-conditioned and keyframe-based approaches. Our qualitative results show that baseline methods often lack diversity in frame composition and struggle with prompt alignment. In contrast, our method produces a variety of shots and maintains consistency throughout the scene. We also address the reappearance issue common in keyframe-based methods, demonstrating that our direct video generation effectively resolves this problem. For quantitative evaluation, we assess visual quality, temporal consistency, and semantic coherence. We use VBench for shot-level quality assessment and conduct user studies to prioritize cross-shot consistency. Our method performs slightly below visually conditioned baselines in visual quality but significantly outperforms them in semantic alignment, showcasing our strength in maintaining scene-level coherence. Section Summary. In this section, we present a novel approach to generating multi-shot videos from text prompts by unifying visual conditioning and diffusion samples, allowing for dynamic dependencies between shots and improved cross-shot relationships. Our method enhances auto-regressive generation through causal attention fine-tuning, enabling efficient use of cleaner history samples while maintaining scene-level coherence and superior semantic alignment compared to existing techniques. Section: Ablative Studies. In this section, we discuss the training and inference behaviors of long context tuning, LCT. We examine single-shot generation after LCT, noting that our proposed LCT does not add extra parameters but enhances the model's capabilities within the same framework. It is crucial for us to determine if LCT affects the pre-trained single-shot generation ability. To investigate this, we synthesize videos using a standard set of prompts with models before and after LCT, evaluating them with VBench. Our results show that the model after LCT consistently performs better across all metrics, suggesting that LCT not only maintains but may also improve single-shot generation. We also explore the effects of different inference modes. Our approach allows for joint generation and auto-regressive generation for bidirectional models, as well as auto-regressive generation for context-causal models. We assess the quality of videos produced by each mode, finding that joint generation leads to better text alignment compared to auto-regressive settings. This improvement likely arises because, in auto-regressive modes, later shots can use earlier information as a reference. Additionally, we observe that the context-causal architecture shows better adherence to historical conditions than the bidirectional model, which we attribute to its causal attention mechanism that prioritizes earlier information. Regarding history conditioning, in auto-regressive inference, we introduce previously generated samples as conditioning inputs, which can be perturbed to a certain noise level. Using clean histories preserves information but can lead to errors accumulating in subsequent samples. We analyze the impact of conditioning time steps, finding that even with a high time step, significant details are retained, although some high-frequency details may be lost. Our analysis indicates that lower conditioning time steps can lead to rapid quality loss, while higher time steps help maintain quality at the expense of historical fidelity. Therefore, we choose a conditioning time step between 100 and 500 to balance long-term quality and historical accuracy. We also evaluate how effectively we can adapt a bidirectional model to a context-causal architecture after LCT. By tracking performance during adaptation, we see that initially, the model generates frames with poor identity consistency. However, after just 1,000 updates, identity consistency improves significantly, reaching quality similar to that of the final 9,000 step checkpoint. This rapid adaptation is likely due to the conditioning mechanism of the bidirectional model, which allows for a smoother transition to the unidirectional flow of the context-causal architecture. Finally, we discuss several new capabilities that emerge after LCT. Our model supports diverse conditioning with images and videos, allowing us to generate narrative continuations from existing videos. Notably, even without specific training for this, we can create coherent videos by combining separate identity and environment images. This ability stems from the model's understanding of visual relationships learned during training, providing a more generalizable approach to compositional generation. Additionally, our model allows for interactive shot extension, enabling us to connect existing content with desired future content seamlessly. This method can extend a single shot into longer durations while maintaining visual consistency. We also facilitate interactive multi-shot development, allowing directors to shape content progressively based on previously generated footage, which enhances creative decision-making with immediate visual feedback.